Hi everyone, in today's lecture we are going to see what is amplitude modulation. So the topics which we are going to cover in this lecture is what is amplitude modulation and how to represent the amplitude modulated wave in the time domain, and also we are going to see how to represent the amplitude modulated wave in the frequency domain and what is the modulation index. So before going to what is amplitude modulation, let us see where we use this amplitude modulation techniques. In the previous lectures, we have discussed about the communication system. So whenever I want to transmit an information to the longer distance, so at the transmitter side, the information which is to be transmitted is modulated. So once we do the modulation, the signal or the information can be transmitted for the longer distance. So amplitude modulation is one of the techniques which is used to modulate the information at transmitter to send it for the longer distance. So by definition, what is amplitude modulation? So amplitude modulation is nothing but the amplitude of a carrier signal varies in accordance with the instantaneous amplitude of the modulating signal. That means we are going to vary the amplitude of the carrier in accordance with your message signals. So where carrier is a high frequency signal and message signal is a low frequency signal. So with the process of modulation, we are converting or we are sending the information on a high frequency signal, or we are doing the modulation of a high frequency signal to transmit your information which is there in your message signal. That is, which means the amplitude of the carrier signal containing no information varies as per the amplitude of the signal containing information at each instance. So it is a continuous wave modulation. That's why we are saying that at each instance, the signal is getting modulated in terms of your amplitude. So this is what the amplitude modulation by definition. Let us see how amplitude modulation is done. Now look at this waveforms. So whenever I want to do the modulation, so I require the information which is to be transmitted. That means a modulating signal or message signal, or we can say that it is also called as a baseband signal. So this information I want to transmit. So I am, as my modulating signal is a low frequency signal, I am taking a carrier signal. So carrier signal is a high frequency signal which I am using. So the amplitude of your carrier is varied in accordance with the amplitude of your message signal. So that is what we call it as amplitude modulation. So when it is modulated, you'll be getting a waveform which is shown like this. Means the frequency of your carrier wave is not going to be changed, but the amplitude of your carrier is at each and every instance. At each and every instance, it will be same as that of your information signal. You can see here. So the modulated signal contains two envelopes with an imaginary line. You can see that in the figure. Modulated signal, a dotted line is mentioned as an envelope in the positive half and negative half of your modulated signal. So it can be observed that the positive and negative peaks of the carrier wave are interconnected with an imaginary line. You can see here the imaginary line is nothing but the dotted line which is mentioned. So this line helps in recreating the exact shape of the modulating signal. That is nothing but your message signal. So this imaginary line on the carrier wave or modulated signal is called as envelope. That means Your signal will have the envelope will be having the information of your message signal in the form of your envelope. So now let us see how we are going to represent this modulated signal in terms of your time domain. That means here we are going to take the information signal and a carrier signal, and what is the standard equation we are going to represent about the third waveform. Whatever the third waveform we have shown here, that is a modulated signal. So I am going to take a message signal and a carrier signal in time domain representation. And when it is modulated, what is the equation we are going to get for your modulated wave? That is, we are going to show in your time domain representation. So let us consider a modulating signal. What is that modulating signal or message signal, which is a continuous time equation, that is m of t is equals to am cos of 2 pi fmt. Already we have discussed earlier also, where am is the amplitude of your message signal and fm is the frequency of your message signal, and your fm is always less than your fc. FM is always less than your FC. Why? Because my message signal is a low frequency signal. So I am modulating my carrier, which is a high frequency signal in accordance with your message signal. And we are considering a carrier signal, that is C of t. C of t is equals to AC into cos of 2 pi FCT, where AC is the amplitude of your carrier and FC is the frequency of your carrier. And the condition is like your FM should be less than your FC. Then only, so whenever I want to go for the modulation, a low frequency signal, that is a low frequency signal is to be modulated. So I am considering the carrier to be a high frequency signal. So I am going to vary the amplitude of your carrier in accordance with your message signal m of t. So when I do the modulation, then the equation of your amplitude modulated wave, which is given by s of t, this is a modulated equation, s of t is equals to AC plus AM into cos of 2 pi fmt into cos of 2 pi fct. This is the standard equation of your amplitude modulation. So when the message signal is modulated, the carrier is varied in accordance with your message signal, then the modulated equation will take the form of AC plus AM into cos of 2 pi fmt into cos of 2 pi fct. So now let us see what is that modulation index is. So what is the role of your modulation index in the modulated wave? Based on the modulation index, we are going to say whether how much depth of modulation is occurring when the wave is amplitude modulated at your transmitter side. So the a carrier wave after being modulated, the modulated level is calculated, then such an attempt is called as modulation index. So what is that impact of your modulation index? So whether the modulation is under modulation, over modulation, or exact modulation, that we can get from this modulation index only. So, or in other words, we call it as modulation depth. How much percent of modulation is done, that is calculated using your modulation index. It states that the level of the modulation that the carrier wave undergoes. Level of means whether it is less than 100% or equals to 100% or greater than 100%. That is what the under modulation, exact modulation, and your over modulation. So as we have seen in the previous slide, uh, that we have given the equation, that is S of t is equals to AC plus AM into cos of 2 pi fmt into cos 2 pi fct. So this equation we can rearrange by taking the AC as common, So we have taken the AC as common and we have written it as 1 plus AM by AC into cos 2 pi FMT into cos 2 pi FCT, where your AM by AC, what we call it as your modulation index, which is represented by your mu. So S of t is equals to AC into 1 plus mu cos of 2 pi FMT into cos 2 pi FCT. So where your mu is called as a modulation index, which decides how much amount of modulation is done. So where mu is a modulation index and it is the ratio of your AM by AC. So when you calculate the ratio of voltages, that is amplitude of message signal to that of your amplitude of your carrier, that gives the modulation index. So let us see how what is the impact of your modulation index when the modulation index is less than 1 or equals to 1 or greater than 1. Now, by definition, as we have said, like a modulation index is nothing but the ratio of your AM by AC. So we can calculate the value of modulation index by using this above formula. So when the amplitude of the message and carrier signals are known. So unless and until you know the amplitude of your message signal and carrier signal, we cannot calculate the modulation index. Now let us further proceed how what is the impact of modulation index on amplitude modulation. So as we know that the modulation equation, as we have seen just now, that is s of t is equals to AC into 1 plus mu cos 2 pi FMT and cos of 2 pi FCT. So with this equation, if your modulation index is less than 1, if the modulation index is less than 1, let us see. So if that ratio of AM by AC, that is, if the value of your modulation index is less than 1, then let us take the example like the modulation index is zero point 0.5. So if the ratio of AM by AC is less than 1 or modulation index is less than 1, then the modulated output would look like below. So you can see the waveform. So here, if it is 0.5, if it is zero point 0.5, already we have written a code for amplitude modulation in the MATLAB and we have generated the equation, the waveform here. So the waveform will be looking like this. So this type of modulation, what we call it as under modulation. Such a wave, what we call it as your under modulated wave, means there is an impact of modulation index. That is, if the amplitude of message signal to the carrier signal, if it is less than 1, the output of your modulated wave would look like this. So now let us see if the modulation index is greater than 1. Sorry, if the modulation index is equals to 1, what is the how the output look like? So if the modulation index is equals to 1, then we call that one as your exact modulated wave. What is that? We will be calling it as your exact modulated wave. So if you look at the waveform, so it will be having, or in other words, we can call it as a perfect modulation. So where you can see the output of exact modulated wave will be looking like this. Suppose if the modulation index is greater than 1, if the modulation index is greater than 1, how the waveform look like? So if the modulation, when the wave, when the voltage of your message signal is 3 and when the voltage of your carrier is like 2 volts, we'll take the example like the modulation index is 1.5, then the wave will be a over modulated wave. So then the output will be looking like this. So in this, what you are observing, there is an increase because of the increase in the modulation index. There is that the carrier is experiencing a phase reversal. So here the carrier is experiencing a phase reversal. So as the value of modulation index increases, that is, if it is increasing greater than 1, then the carrier experiences a 180 degrees phase reversal, which causes an additional sideband hence the wave get distorted. Such kind of waves during the demodulation process, we will not be able to retrieve it back. Such an over-modulator will cause interference which cannot be eliminated. So, when the modulation index is crossing the 1, it is called as over-modulation, and your wave cannot be retrieved back, or the information cannot be retrieved back at your receiver, and which causes your interference. Now, let us see what is the frequency domain representation of your modulated amplitude modulated wave. So already we have seen that the time domain representation of the equation S of t is equals to AC plus am cos of 2 pi fmt into cos of 2 pi fct. So to convert a time domain represented equation into a frequency domain representation equation, we need to apply the Fourier transform. So if we apply the Fourier transform for a cos or sinusoidal signal, that is cos of 2 pi fct, I'm taking example of cos of 2 pi fct, then it is represented as del of f minus fc plus del of f plus fc. So to convert a time domain equation into a frequency domain equation, we use the Fourier transform. So when you apply the Fourier transform to the above time domain equation, then S of t is equals to AC by 2 into del of f minus fc plus del of f plus fc plus Ka AC by 2 into m of f minus fc plus m of f plus fc. This is what the frequency domain representation equation. So here with the frequency domain representation, we are going to show you how the sidebands and carrier will apply, will look like uh, in the next slides. So, suppose let us take that the message signal or the baseband signal S of t is having a band limit of minus W to plus W. Then your figure 1, that is here, this is the frequency domain representation of your message signal, which is m of f, and on x-axis we are showing the frequency. So it is having a band limit. We are taking the example here, that is minus W2 plus W is the bandwidth of your message signal. So then the spectrum of AM wave, then the spectrum of your AM wave will look like that is shown in your figure B. That means it is having, from the figure, it is very clear that it is having the upper side band in the positive frequency and a lower side band, and along with your carrier, there is a carrier also. So it is on the positive side, and the negative side also we can see a lower side band and an upper side band. It is having three signals. One is a carrier signal f of c, and it is having the upper side band, and it is also having a lower side band. So we have three informations in the modulated wave. One is a carrier, the other is the upper side band, the other one what we have is your lower side band. Let us move further and see. So we'll analyze this frequency domain represented equation. So from the Fourier transform of the equation, that the spectrum S of f of your AM wave, which is shown in your figure B, this is the frequency domain representation. This is for the case where you have your frequency of your carrier signal is always greater than 1. We have seen earlier also in the previous lectures, like this is one of the condition which is to be used to get your amplitude modulated wave. So the spectrum consists of two delta functions. So one is uh, del of f minus fc, that is we have seen in the previous equation, that is del of f minus fc, and del of plus del of f plus fc, f plus fc. So two delta functions, the frequency domain representation is having, and weighted by a factor called as AC by 2. You can see here there is a AC by 2 and a del function del of f plus fc and del of f minus fc, and occurring at your both the plus or minus fc. One is at your plus fc, the other is at your minus fc, and the two versions of your baseband spectrum translated in the frequency by plus or minus fc and scaled an amplitude of your what Ka into AC by 2 into m of 0, or having an amplitude of Ka AC by 2. So what is the amplitude? So with the modulated equation, the amplitude of your sidebands is given as 1 by 2 Ka into AC by 2. So it is having two delta functions. It is having two delta functions. One is del of f minus f plus fc, the other is del of f minus fc, and having a weight of AC by 2 and having an amplitude of half of Ka AC by 2. Now, let us move further and see what are this, where this upper sideband and lower sideband are located. So, as a result of modulation process, the spectrum of message signal m of t for negative frequency extends from your minus w to 0. That is, from here to this point, it is extended, that is your negative frequencies of modulated signal, and becomes completely visible for positive, and it is visible for positive, that is means it is measurable, and positive frequencies visible for positive frequencies, provided that the carrier frequency satisfy the condition, that is fc greater than w. So the condition to have and modulation is always the frequency of the carrier should be greater than that of your message signal. Sorry, that is fc should be greater than your w, and your mu value should be always less than 1, or we can say it is greater than 1. So if it is sorry equals to 1, if it is greater than 1, there is a interference which is occurring, so we cannot retrieve back the original signal. So what are that upper and lower sidebands are where we have located? Let us see. So for positive frequencies, that is from your 0 to Fc plus W, or 0 to Fc. These are the positive frequencies. The portion of spectrum of AM wave lying above the carrier frequency. That means from here to this one. So I'll draw it from this Fc to Fc plus W. This frequencies for the positive frequencies. That is for positive frequencies above your Fc. So it is referred to as your upper side band. So this is referred to as your upper side band. So this part, whatever you see here, this part we refer to as your upper side band. And whereas the symmetric portion below the FC, that means the second part, uh, you can see here. So the symmetric part means this part. This part is referred to as your lower side band. So for negative this is what we have seen for your positive frequencies. Now let us see for the negative frequencies. For the positive frequencies, what we have said, above your FC, above your FC, we call as upper side band, and we call below your FC, that is from your minus FC, sorry, FC minus W to your FC. FC. We call it as your lower side band, that is LSB. Whereas FC or FC to FC plus W. Fc plus W, we call it as upper sideband on the positive frequencies. Positive frequencies. Okay, so similar way, if you look at the negative side of your negative frequencies, so the spectrum, what we say, the spectrum which is spectrum below minus Fc. Below minus Fc means from here to here. So the upper, sorry, for negative frequencies, the upper sideband is represented by a portion of spectrum which is below minus Fc. That means it is from minus Fc to here. This one is represented as your upper sideband. Whatever you see in the figure, this is represented as your upper sideband. And the lower sideband portion, above your Fc. So above your Fc means this is in the negative frequencies, this is the above Fc. So this is represented as your lower sideband. So if you are not maintaining the condition, that is Fc is greater than your W, if you are not maintaining, these sidebands may overlap. How they will overlap means these sidebands may overlap like this. So if you are not maintaining the Fc minus Fc greater than your W, so the two sidebands, the lower sidebands may overlap with one another. We'll see still. So for the positive frequencies, the highest frequency component is nothing but your Fc plus W, that is, which is equals to Fc plus W. And for the lowest frequency component in the positive frequencies, that is Fc minus W. So the difference between these two frequencies is nothing but what we call it as your bandwidth. And for AM wave, the bandwidth is given as B is equals to 2W, that is Fc minus W or plus W, sorry, Fc plus W higher frequency minus Fc minus Fc minus W. So which results in 2W. So this is the bandwidth of your modulated wave. From this frequency domain, it is very clear that the modulated wave bandwidth is twice that of your message signal. The bandwidth is twice that of your message signal. So with this, we'll conclude. In the next lecture, we are going to see what is a power calculation, the power consumed by your amplitude modulation, and we'll also work out on some more examples which